Okay, for part 2, we are looking at radiation and Newton's law of cooling. And there's some things in the chapter that we kind of skip over, okay, so skip over it. So let's see what this is about. So radiation is the transfer of energy from one place to another by electromagnetic waves. And electromagnetic waves are like ordinary light. Those are an electromagnetic wave. And what that is when you have a wave that is made up of electric fields and then it also has magnetic fields that go along at the same time. And that's what an electromagnetic wave is. And that's a really long word to write. So we also say EM wave. That's a short wave to write it. Okay. But electric fields, magnetic fields, and we'll find out more about those in after we do electricity. Okay. So various types of electromagnetic waves. So there are radio waves. And then there is also microwaves, right? So you cook your food with microwaves. And then there's infrared rays. And then we have visible light waves. So going from red to violet. And then we would have, after that, we would have ultraviolet, X-rays, and finally, gamma radiation. So those are all various types of electromagnetic waves. The only ones we can see are visible waves. But of course, we have different types of detectors that can detect all the other ones. Now, one thing about radiation is that it is a wave. And we'll talk more about it in later chapters. So it has a wavelength, but also a frequency. And those are inversely proportional. So in other words, when one gets larger, the other one gets smaller. So when you have a low frequency vibration, like this one, then it has longer wavelengths. So wavelength would be one complete wave. So that would be your wavelength. And this symbol lambda is what is a symbol used for wavelength, but we won't use that. Actually, we'll be using it in the sound chapter. So chapter 20 is and so. Okay, so lambda looks like an upside down Y. And over here, we have high frequency vibrations. And so they have a shorter wavelength, right? So inversely proportional. So high frequency is also proportional to energy. So higher frequency, higher energy. If we look back at this list on the previous page, you might say, which one is more higher energy? Well, gamma radiation is the highest. And that's why, like in the movies, the Hulk, he's damaged by gamma radiation, right? Okay, so that is the highest frequency, which means it has the shortest wavelength. And radio waves are the lowest frequency, and they have the longest wavelengths. They can be miles. Whereas a gamma wave has a wavelength that is about the size of the nucleus of an atom. Okay, so all objects that are above 0 Kelvin degrees, they give off radiation. And that radiation that they give off depends on how hot they are. So electromagnetic waves can be given off, or infrared, or visible. And the thing is that these waves can transport heat through a vacuum. So you don't have to have molecules carrying the energy along like we were talking about for conduction and convection. The energy here is in the wave itself that radiates through space. And, if you've ever stood outside and let the sun hit on you and you get hot, well, that's because you're getting energy from the sun, from those light waves that are hitting you. And if you get a sunburn, well, that's the ultraviolet rays that have brought energy to your skin. So anyway, as things get hot enough, they start to produce even visible light if they're hot enough. So we would say things are red hot or white hot, and those are things that are pretty hot, hundreds of degrees in temperature, or thousands, like the sun is about 6,000 Kelvin, and it produces all types of light. So it's a white hot, because white is a combination of colors. Now here we have a person who is being seen in infrared, because people, we aren't too hot. We don't glow in visible light. We glow with infrared light. And most objects on the earth glow in infrared. Only a tiny percentage of things are hot enough to produce light. Okay, so right now as you sit there, you are radiating infrared light. And we will use an infrared camera to look at things with infrared light. Okay, now, as I said, every object above absolute zero radiates. The sun, which is about 6,000 degrees Kelvin, radiates visible light, and ultraviolet and some other stuff too. Anyway, so it has a that would be a higher frequency than the infrared light, which is what most of the things on planet Earth produce. So on planet Earth, the temperature's on average about 320 Kelvin. So it's much, much cooler. And so objects radiate with infrared. Most objects. Okay. So there's infrared waves. We also call them terrestrial radiation, because Terra is the name for Earth. Whereas from the sun, it's visible light, and we call that sometimes solar radiation, because it comes from Sol, our sun. Now, we can't see infrared radiation with our eyes. Okay, that's why we have cameras. Here's some charts showing the sun's radiation. So the sun is 6,000 kelvins, and it peaks actually kind of in the yellow greens or the greens, but it has all the colors of light that we expect. So violet, blue, green, yellow, orange, and red. All together, then that makes it look white, or maybe a little bit yellowish. But yes, it's pretty much white light that comes to us from the sun. Now, the sun does produce some other things. So it will produce some infrared and some ultraviolet and some other things. But mostly it produces visible light. As for the planet Earth, we average about 288 Kelvin. And so because of that, we're pretty cool. And so what that means is that we just produce infrared radiation. And if you look at the wavelengths here, the wavelengths of the the infrared radiation, that's 5, what are called micrometers. This is 0.5. So the wavelengths are about 10 times greater from the planet Earth than they are on average from the sun. Okay, so longer wave radiation from the Earth, short wave radiation from the sun. Not the shortest, it's not a gamma ray, but it is shorter than terrestrial radiation. Okay, and here's just some pictures of objects, metal that is being heated in a furnace, and you can see that it's glowing red hot and white hot as it heats up. Here's some people seen in infrared. So as we glow, and the hotter we are, this camera interprets that as red for the hottest and blue for cooler. And this is going between 94 degrees and 70 degrees. And you can see that the faces are pretty bright red. We've got temperatures close to 90 there. But you can see the clothing blocks the radiation. That's why we wear clothing, to keep our heat close to our body. Hair also is keeping heat onto our body, right? So somebody's got a hoodie there, somebody has a hat. This guy's a little bit balder, okay? So you see a lot more of radiation there. Here's a street scene. And what we've got here is we've got some cars that are being heated up by the sun. And we've got some people on a sidewalk. But you can see they must be in the shade. It's a lot cooler on the right side of this street. But we also have trees. So trees, even though they are cooler than the cars, they still are producing infrared radiation. And if you ever get an infrared camera for yourself, they're cheap enough now for everybody to play around with almost. You can do some cool effects with it. So people put different colors in and get different images. Okay, so we were talking about how temperature and creates different. Different temperatures create different frequencies. As an object is heated up, it radiates at different frequencies. And this is the sort of picture that is famous for physicists, and showing how as temperatures heat up, their peak frequencies that they create increase. So the red line is 1600 Kelvin, and the green line is 2400 Kelvin, the blue line is 3200 Kelvin. Now the red, the green, the blue are not the colors we're talking about. It's the frequencies of the light which is increasing. So frequencies of the electromagnetic wave. Now if we get to 6,000 degrees would create something that peaks in the visible region, right? That's what we were talking about. That's the sun. The sun will peak at the visible region. Okay, so if we have 6,000 Kelvin, it's an even higher frequency. Okay, now we're going to talk a little bit about emission and absorption. There's more in your book, but the idea is that objects can both absorb and emit radiant energy. So when you're sitting, okay, in the sun, you are absorbing heat energy, right, from the sun. But you're also emitting energy because your body is producing infrared radiation. So anyway, so your car, most things usually have a balance of incoming heat and energy that is being radiated away. However, if an object absorbs more energy than it emits, it's called a net absorber. And so when you put a cake into the oven, it's going to absorb more energy than it emits. If it emits more energy than it absorbs, it's a net emitter. So you bring that hot cake out of the oven and it starts to radiate heat away and it cools down. And you've probably heard that dark objects will get hotter than light objects. So a lot of people like white cars because they don't get as hot as a black car. And that's true. Dark objects are dark because they absorb energy, and white objects are white because they reflect light away, right? So white things will tend to reflect light. They don't get as hot. And they are called poor absorbers and poor emitters also when they are light in color. Whereas dark objects, they're good absorbers of energy. If you heat them up, they're also good emitters. So if I heat this jug up, it's a ceramic jug, then it will radiate heat very well. Okay, so what happens is that if objects are hotter than their surroundings, they will be net emitters and they will cool. If it's colder than their surroundings, then the object will be a net absorber and it will get warmer. Okay, so what we're going to look at next is what's called Newton's law of cooling. So Newton's law of cooling is the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. So you have a hot apple pie. Do you leave it in the oven to cool? No. You take it out and you put it somewhere to cool. And if you want it to cool fast, you might have to put it in the freezer. And also something interesting, now that we're talking about insulation and stuff, a warmer house more quickly leaks thermal energy than a cooler house. So in other words, if you've got your thermostat right now, or during the winter, if your thermostat is set on 72, okay, versus setting your thermostat on 68, the house that's set on 72 will radiate more energy outside. So it'll be more expensive to heat it by having it at that higher temperature. Whereas the house at 68 is going to radiate less energy to the outside. So it's easier to maintain its temperature. And so the same thing right now with houses that we're cooling is again, if you're trying to set your house to a low temperature, so if you're trying to set it for 64 or something during the summer, well, versus 67, well, the house that's 64 is constantly going to have heat coming in at a faster rate than the house that is only 67. Okay, so this is something that has to do with your bill. Okay, so keep your temperatures more moderate, and you will be paying less for energy. Okay, but let's see how this Newton's law of cooling works. Okay, so back to this. All right, so rate of cooling is proportional to the temperature difference between the object and its surroundings. Okay, so let's go do an example, because this is like you might have in a test. Okay, so let's say that we have bowls of soup. And let's say that we have 3 bowls of soup. And they're all sitting in a room where the temperature of the room is 20 degrees Celsius. That's room temperature. Okay, and one of the bowls is 40 degrees Celsius. The other one is 60, and the other one is 80. Okay, so what we want to look at is the difference, right? We want to go and look at delta T, the temperature difference between the object and its surroundings. So let's calculate those right now. So for the bowl on the left, we've got delta T is going to be 80 minus 20, right? So that's going to be 60. The bowl in the middle, 60 minus 20, so delta T is 40. And the bowl on the end, we've got 40 minus 20, so delta T is 20. Okay, so that's the temperature difference between the object and its surroundings. Okay, so what was Newton talking about? Let's go back and look at the words again. The rate of cooling of an object is proportional to the temperature difference. Okay, so what's the rate of cooling? Let's say that the bowl on the right was radiating 2 joules per second. Okay, now the middle bowl has a temperature difference that's twice as much as the bowl on the right, right? So the bowl on the right is 20 degrees difference. It's radiating 2 joules per second. So the bowl in the middle is going to radiate at twice that rate. So it's going to radiate at 4 joules per second. Okay, and the bowl on the end, since it's 60 a temperature difference, that's 3 times as much as the first bowl. So what's going to happen is it's going to radiate 3 times as much energy per second. So it's going to radiate 6 joules per second. Okay, so that's how it works. You're saying that the rate of energy transfer is going up. Okay, and so rate is per second. All right, so anyway, so you've got some homework problems similar to this and one on the test too. So make up your own bowls of soup and see what you can do with it. Okay, now Newton's law of cooling is also Newton's law of warming, because things warm up based on the difference between the temperature of the object and the environment too. And so like ice cream, if you've eaten it during the winter in an air-conditioned restaurant, then you can eat it comfortably and it'll last for a while. Whereas if you're outside on a sunny day, you know, the ice cream starts to melt, and so it can make a real mess, because there's a bigger temperature difference between the object and its environment. And that means the energy is going to go into the ice cream at a faster rate. Okay, so that's all we're going to do on this. And we are going to cover, we are skipping chapter 17. I'm not doing a lecture on that. We're going to do a tiny mini part of chapter 18. So stay tuned. Okay.